right, so hello everyone. So my name is Omar Nofal. I have been at FIU for 2 years. This is the third time to teach advanced structure analysis at FIU. I used to teach this class at other universities. First, I hope that you guys had an amazing summer. I'm just gonna introduce myself, and maybe because we have like smaller class, you guys tell me your name. If you have a master's, doing your PhD, tell me something about yourself. So I got my bachelor degree in 2013 from Cairo University, and my master's is in structure analysis, basically seismic and wind load design for tall buildings from Cairo University in 2017. I got my PhD from Colorado State in 2021 in natural hazards and community resilience. Then I did a postdoc for 1 year also in the same focus, community resilience with multi-hazard hurricane. I joined FIU in 2022, that was like two years ago. And I have taught different classes. I taught undergrad classes like engineering dynamics. I also taught like advanced structure analysis. And I'm teaching also a class, it's called Risk and Reliability next semester. It's kind of more if you are into natural hazards or you want to get into how we do analysis at the building level, community level, studies that work, like if you're going to work for an insurance company with a civil engineering background, you should have risk and reliability background. So, but yeah.
Is there an online class?
No, it's in person.
In person as well?
In person class.
Nice.
It's usually higher level, so it requires, I don't know, structure analysis background, statistics background. I usually teach statistics, but also if you have good statistics background, it's gonna help you. Like recently, like most of being a civil engineer is very good, or a structure engineer, you design building and everything, but going to the next level, how to estimate the probability that you have a specific level of damage, help insurance companies to estimate their premiums based on the occurrence of a specific hazard that is gonna happen in 100 years, or the building status, like building information, like when this building was built, is it up to code or not? So all these information help you to understand what is the probability that this building is gonna fail if a hurricane Cat 3 happen. So that's help insurance company. So that's the main focus. So I teach basically some statistics stuff and also the structure engineering stuff with GIS, programming. So it's kind of high level class. That's just a background about the classes that I teach at FIU. So that's basically about me. This class, Advanced Structure Analysis, requires you to have a basic structure analysis, like how to get reactions on beams, how to solve for normal force diagram, shear force diagram, and bending moment diagram. You should have all these basics for beams, frames, trusses. And then once you have this background about solving determinate the structure, what we are gonna do in this class, teach you how to solve indeterminate structure. But first I'm gonna teach you how we can, what are the determinate and indeterminate structure, how to distinguish them, and if we distinguish that a structure is indeterminate, how can we solve it? So that's what we are gonna learn multiple methods that allows us to solve these types of structure. And I'm also gonna teach you software. I'm not sure if you guys have worked in software before, ETABS, SAP 2000, whatever software that you have been using in industry. So I'm gonna teach you how the software is doing analysis and how we do the analysis with our theories and compare between them and see if they match or not. So that's things that we're gonna do in this class. The class is gonna have, I believe the grades is divided 10% homeworks, 15% quizzes, maybe 3 quizzes during the semester, and 50% on midterms. We are gonna have 2 midterms. And there's no final exam, but there's a final project that's gonna be a group project. This project is gonna use the basics that we are gonna teach in the class about seismic engineering, lateral load design, structural dynamics. I'm gonna teach a little bit about them by the end of the class and give you the knowledge that allows you to analyze tall buildings. And we are gonna have maybe 60-story tall building and analyze this building. And when I say analyze, not to design, we're not gonna design sections like reinforcing concrete or something. But what we are interested in, we're interested in the internal forces inside the structure. What is the normal, what is the shear, what is the moment, what things that we can do for this structure that allows us to decrease these internal forces so that we can have more economic design, okay? So that's what the things that I'm gonna teach you in this class. But first, we are gonna start with determinant, indeterminate, and one strategy that I used when I taught this class at first at FIU, I finished all the theories and then did all the software at the end, like half the semester theories and half the semester is software and design. It didn't work that well. It worked, but I mean, like, students, because it's a lot of information to digest for the half of the semester, and I did in the next semester, I was combining between both, like 2 lectures on the board and 1 lectures on the computer, teaching the students to software, and then back to the theories. So we take like kind of software break. So that worked, the students like it, so maybe we will follow the same approach, like 2 lectures on the board or 3 lectures, and after I introduce a little bit of basics, I go to the software and then teach you how to do this on the software, and then get back so that we have kind of a little bit of breaks between lectures and less information to digest, because, you know, like, it's much easier for you to deal with computers and softwares. All right, so class rules, like if you got a phone call or something and you want to take it, you can leave anytime. If you want to leave anytime during the class, you can do it. No texting during the class, your phone is your pocket. If you want to text or you go, it's okay to go outside the classroom, text, call, do whatever you want and get back. So that's the classroom rules. I'm not sure if you guys checked the Canvas page for I uploaded lecture 1, lecture 2, homework number 1, and also the syllabus. Did you guys see it on Canvas? So I'm gonna send an announcement today on Canvas and giving you all the links how to access. What I do, all my lectures are recorded, like I try to record them by my phone, upload them on YouTube, so you'll have access to the recorded lecture. But some of you are like, okay, the class is recorded, so I'm not gonna attend the class. So for the quizzes, I sometimes give hints during the class that might not record it. Like, I give hints about how the quiz problem is gonna be solved or something similar. So it needs you to be attended in the class. So quizzes, the 15%, basically is made for who is attending the class. Because I'm not taking attendance or anything, but basically if you attend the class, you will know how to solve somehow, I'm not giving the problem, you will know somehow how to solve the problem. So that 15% is made for the people who is gonna attend the class. So the class is gonna be recorded in my phone, and also the lectures, the notes, I have them written and uploaded. I will try to upload them before the class like the way that I did today, but maybe sometimes I will get busy, so I upload them just after the class. When you go home, you'll find them. But I will try my best to have them written and upload it before the class. So if you wanna print them, if you wanna look on something, do something, so get them on your iPad and watch them so that you can focus on the board. So whatever teaching method that you would like to do, if it worked for you that you can print them and attend the class and just watch what I'm doing, it's okay with me. But it's better, like for me, it's better to write while the instructor is explaining the concept so that you follow what I'm doing. But if you have something written in front of you, you might lose attention. So we are all different, so do whatever that's work for you. Okay, so for today's lecture, I introduce myself, so it's your turn to introduce yourself. So we'll go this way.
I'm Gabriella. I have a bachelor's in mechanical engineering, and I'm getting my master's in civil engineering and structural analysis area.
So you have a bachelor in mechanical?
Yeah.
But you have structural analysis basics, right?
I do, yeah. I just took it in the summer. Yeah.
Okay.
I had some of the features in classes, so I just took it.
Sounds great, yeah. All right.
Hi, my name is Daniela Lazarezas. I'm going straight for my master's in structural.
Structural engineering? Thanks.
Good morning, everyone. My name is Mustafa. I'm from Bangladesh. My bachelor's is in civil engineering, and I did my MBA also in operation and supply chain management. I have 7 years of working experience as a structural engineer in my native country. So I did my master's also from Wayne State University in civil engineering, and I'm here for my PhD and working with Dr. Novel. So I'm looking forward for this new venture.
My name is Masood Fahy. I'm a PhD student working with Dr. Merabi.
Nice to meet you.
My name is Ryan Manalo. I'm like the first person. I have a bachelor's in mechanical, and I'm taking my master's in structural engineering.
Can I know the motivation about shifting from mechanical to structure?
I got a graduate assistantship with one of the professors, and so I had to do civil engineering. But I mean, the area that I want to go, like, it doesn't matter much. So
Okay.
yeah.
So you guys, like, after getting masters in structure, are you gonna work in a structural engineering or mechanical engineering?
I want to go back to mechanical
Okay.
engineering. Yeah.
Nice.
My motivation is I'm currently working as an MEP engineer. However, I have dealt with my peers, civil engineers
Yeah.
in the firm, and I kind of
We
gotta
are
get into
cousins
their
at the side,
perspective
yeah.
as well. So that's why I'm kind of combining my both experiences,
That's
MEP and being in structural as well.
That's great.
My name is Shivam Mishra. I'm from Mumbai. I did my bachelor's in India, did my master's at University of Buffalo in New York, and I'm here for my PhD. It's my first semester.
Good. Yeah. What is your PhD is gonna be in?
In Wind, I'm working with Professor Chaudhary.
Chowdhury. Oh, okay. Nice.
My name is Kevin, from Peru. This is my first master, and right now I'm just studying.
Okay.
Hello everyone, my name is Paula Martinez. I'm enrolled in the 4+1 program, so I'm completing both my bachelor's and my master's in civil engineering. In my master's, I'm focusing in structural engineering, and I'm from Colombia.
Good morning, everybody. I'm Diego Piazza. I graduated this spring and I started working in structural engineering since January. So I came here looking for a little bit more of knowledge, theoretical knowledge that I can apply at work. So I'm starting my master's with this class.
Hey, my name is Javier Martinez. I'm from Cuba. I'm in my senior year of the undergrad, but I'm doing the 4+1 as well with the focus on structural engineering.
Amazing. All right. So sounds like a lot of focus on structural engineering. All right. So let's just start with structures. Yeah. Just remember the text rules. Your phone is in your pocket. Okay. So today our lecture 1 is about how we can differentiate between determinate and indeterminate structure. But before we do this, let's dig into something. It's right here. Difference between determinate and indeterminate structures. Do you guys know the difference between determinate and indeterminate structures? Have you guys heard about determinate and indeterminate? Okay, so what is the difference?
So determined structures can be found with equilibrium equations, and indeterminate structures is like a step forward, a little bit more.
Exactly. So that's very close. Excellent. So what we have here, so if we have a structure like this and a structure like this. All right. So let's think about this hole. To cover this hole, we can cover it with this slab. We can make the end condition of this slab something like this. We put it on a hinge, or put it on a roller, or we can make a frame like this. So they both are gonna serve the purpose of construction, or serve the purpose of providing covering or sheltering to the area that we are working on. But there's different ways that we can do them. It's either we can do them this way, or we can do them this way. There's other different ways, but I'm just putting these as an example for determinate and indeterminate structure. But there's benefits, there's ups and downs, there's pros and cons for each one of them. So can we list the sum of the pros and cons for each one? Like, let's just start with number 1. These are old. All right, so let's just start with number 1. Determinate structures. What about determinate structures? Number one, they are much easier to solve. Much easier to solve. Is the handwriting good? Do I need to make it bigger?
I can see.
Okay, sounds good. Much easier to solve. Why? Because I can use the equilibrium equation, some fx, some fy, some of the moments, and solve this structure, get the reactions here, get the bending moment, get everything. It's a very, very easy, straightforward. A first year engineering student can solve this. Very easy to solve. Number two, and this is very, very important, no support, no internal forces induced from support settlement or temperature. And that's very, very good. I mean, like, let's assume that we have a foundation here, like isolated footing, and this footing is slid 1 centimeter or 2 centimeter. It's not gonna induce any internal forces in this beam. Why? Because it's gonna make something like this. There's no bending moment, there's no shear force because it's determinate. Okay, and that's very, very good. Okay? And this is for the determinate structure. That's the good things about them. Okay? But you tell me what bad things, I didn't list it here, but you tell me what is the bad things about determinate structure?
There is no redundancy.
There is no redundancy. That's very important to have redundancy in your structure. Let's assume that somehow you lost the friction under your foundation and there is a wind load came this way, this structure is gonna fall apart, okay? So there's no redundancy. You need more reaction so that you can be more safe, okay? So that's, I mean, like, you can't write it as a note because it's not here in the notes. Okay, let's get back to indeterminate structure. Indeterminate structure, what is good thing about them?
They're redundant.
There's the redundancy, right? That's one thing. And what else? How the redundancy is gonna help you to make this structure better? It's gonna decrease the internal forces. Like, let's assume that we have some load on this beam, something like this. The bending moment, do you guys know what is the bending moment value here? WL squared over 8, right? Okay, but let's assume that same load here, there's W here, and there's W here. The bending moment is gonna be higher, bigger than WL squared over 8 or less?
Less in the middle.
It's gonna be less in the middle. Why? If you draw the bending moment on this beam, it's gonna be something like this. You're gonna have a negative bending moment here, and it's gonna be something like this, and this is gonna be, once you solve it, that's an indeterminate structure. Let's not go in details how we solve it, but this is how the bending moment is gonna look like. And the bending moment measured from here to here is WL squared over 8. That means this value is less if you plus these two. So that means the bending moment has been distributed over the beam. So if this cross section has less bending moment, that means less reinforcement, less cross section size, and that's better. It's gonna make your structure more economic. Okay, so what I wrote here, it's less induced bending moment than indeterminate structure. Also, it's more rigid due to the fixation here. More rigid, that means you have redundancy. If this one lost the friction, there is still another foundation that can take over the horizontal load. If this lost rotation, this one. If you lost this foundation, you know, sometimes you find these pictures on the internet, like building is still stable and the foundation doesn't have any soil around it, okay, at some locations. That means it has a lot or a good redundancy. Like there is a very, very, very good columns is taking all the loads. Like let's assume this lost all the foundation here. This structure can still take more load because that's a fixation. Okay, so that's what I have here. And but what is bad thing about them? About these? What else bad thing? It's the settlement. Like let's look here. I said no internal forces induced from support settlement or temperature. If temperature happened for this, like let's say that the sun is hitting this roof all day, it's gonna expand. Once it's expand, it's gonna induce internal forces inside these columns and beams. But here, if this is wanna expand, this roller is gonna go this way. It's gonna expand, it's not gonna restrain it. But if you have a fixation here, there is a restraint that doesn't allow this, so it's gonna make a bending moment on the frame. Same thing with settlement. If this support settled, it's gonna induce internal forces. So both of them are good, but there has pros and cons, okay? But let me tell you something. What is the applications that we see in real life? They have more of these or more of these?
More of these.
More indeterminate structure. Most of the structures that we design are indeterminate. I rarely see determinate structure in real life. Like there are, like sometimes you have a bridge. Like, do you guys see when you have like a road and there's a bridge on top of the road? Sometimes you find something like this is, for example, the column of the bridge, something like this, and then the cars is going underneath the bridge and there is a slab on top here. And usually they make it not attach it to the bridge. Like they put a hinge here, for example, and roller here. And they make it that way because that usually happens all the time. If a car that exceeds the height limit of the road and hit this beam, it's gonna be easy to replace it. So they're just gonna remove it and put the next one. So they don't attach it to the bridge so it doesn't make any collapse to the rest of the bridge, okay? And also help with the expansion and the planning. Like if we are gonna change the planning of the area, you can't just remove it and do whatever maintenance that you would like. Okay, so that's, I believe, a good introduction about indeterminate structure. But as we said, we less see these and more we see these structures. All right, so let's go to the next topic. What I wanna talk about these hinges and rollers and fixations and connections in general, because I want to build a good basics before I start the indeterminate structure. So we all know the end conditions. Do you guys know what end conditions that we have out there? End conditions, I mean supports. What kind of supports that we have out there that we use to represent structures? So you guys know rollers, right?
Yeah.
And hinges, and fix it. What about these? What is the difference between them? If you saw a roller on us, actually in real life, we don't have these. Like when you look at the structure, you're not gonna see this, but we use them to model structure so that we can do structure analysis on them. So these are just representation. So what about this? Like what kind of reaction does it have?
Vertical.
One, it's vertical, right?
Yeah.
And this one?
Vertical and horizontal.
X and Y. How about this one?
X,
Three
Y,
reactions.
And bending.
And moment, right? We have 3 reactions, but we have other ones. I can actually also give you this in a different shape. Like I can give you this, something like this. If I give you the ruler like this, or the hinge like this, how it's gonna be different? For the first one, it's gonna be different. There will be no vertical reaction, and the reaction is gonna be this way, right? This one is not gonna be different. It's just like a change of names, Rx and Ry, right? It's gonna be the same. Like I would say this Ry and this is Rx. Same thing, I would say this is Ry, this is Rx. Okay? But I wanna introduce some end conditions that you might not see before. We have something is called guided support. Have you guys heard about this before? So you will see in the homework or during the class about this hinge or this kind of end condition. This is called guided support, and it's something between fixed and roller. So it has 2 reactions. So it's like this one, but without one. Do you guys tell me what kind of reaction this one could have?
horizontal.
It's gonna horizontal. Excellent. What else? Moment. This way, right? Because it allows the vertical movement. Like allow why? Because I put the rulers in this direction. Sometimes I will give you this support this way. Like let's say I'm gonna make something like this, this. How about this support? What kind of reaction does it have? It's gonna have a vertical, excellent. and moment, because the rollers are in this way, so it allows the movement in the x direction. Once you restrain this movement, there is a reaction. Like let's look at this pin. If I fix it this pin, that means that I restrain the movement in the x direction, in the y direction, and the moment. But once I make a roller here, so that allows the movement here, but I don't allow it to move up, so there's reaction going in y direction. And if I restrain the rotation, so there's a moment reaction. So when you restrain a movement, there is a reaction. When you allow a movement, there is no reaction. So if the movement allow in y direction, so there is no reaction in the y direction. When I allow the movement in the x direction, so there is no x reaction. Once you restrain this movement, there is a reaction. So I wanted to introduce this first. But let me, yeah.
Well, I have a quick question more like into when we are working and designing fixity and stuff. For example, for masonry reinforcement.
Okay.
You know how masonry reinforcement goes like from floor to floor to floor to floor?
Yeah.
When we are designing that, depending on the connections that we make between, we can decide if it's going to be
That's a really good question, and that's actually the next topic.
Mhm.
There is no such a thing of a pure roller or a pure hinge
Yeah.
or a pure fixation. There's no such a thing. There's always a movement. Like if you have a roller, sometimes you can't assume that means that you have a perfectly smooth surface that allows the movement 100%. There's always friction. There is always friction in the side, like there's always friction here, unless you have an ice. Even if you have an ice, it has a friction coefficient. Okay, so that means that there is no pure roller, there is no pure hinge, there is no pure fixation. There is always something in between. But we put fixation because the coefficient of friction is very, very low that make a reaction. Like let's say that we have a reaction here, 100 ton.
Yeah.
Okay, we have 100 ton, but you have a reaction here, 0.001 ton. It's not gonna matter. It's very, very small that you can't neglect it. So that's when we say a roller. So let's actually put this in writing, how we can describe non-perfect hinge or roller or something. So we're gonna talk about rigid and semi-rigid connection. That's gonna take us to what you were talking about. Okay, so let's talk about this topic. Rigid and semi-rigid connections. All right, let me draw this frame. I'm gonna make a frame like this. Oh yeah, I forgot to tell you about one thing before I draw this. Sometimes I give you something in your homework that's something like this. You have something like that. You guys know what is this when I draw in a structure? Intermediate hinge. Okay, it's called intermediate hinge. What is the characteristic of the intermediate hinge?
Releases moment on the side.
It releases the moment in your frame or your structure. Like if you have your structure like this, that means here, if you cut and get a cross section here, you will find all the internal forces, shear, normal, and moment. But once I put this hinge, that means you release the moment. You allow the two joints, like it was like this, that's fixed. So you can't rotate this. Like if this joint is gonna move this way, this one is gonna move this way. So their motion is restrained. Like I'm not gonna leave you, I'm gonna stay with you. If you wanna rotate this way, I'm gonna rotate with you. If you wanna rotate this way, I'm gonna rotate with you. But once you make an intermediate hinge, then you separate the rotation between them. You can rotate whatever you want, and I can rotate whatever I want. But if you wanna go up, I'm gonna go up with you. If you wanna go X, I'm gonna go X with you. That's what intermediate hinge do to structures, okay? All right, so let's talk about this as well. Like if I put an intermediate hinge and I put a spring, have you guys seen this before? This spring means, okay, I am not fixed and I'm not intermediate hinge, I'm something in between. Like if you rotate this way, I might be rotating with you, but not with the same rotation, okay? So that we call semi-rigid connection. So it's not rigid and it's not flexible. Like it's not flexible moving on its own, and it is not rigid that is connected with the other structure. So to represent this, we put a rotational spring. Like, you know, like you connect these two, you try to get like, I don't know, a wire or something and try to connect them so they can move together, but somehow your connection is not as strong as if they are fully connected. So when you hold them, they are making like this. That means they are not flexible and they are not rigid. So it's something between. It depends on the stiffness of this spring. And let's assume that the stiffness of this spring is infinity. What does it mean? Does it mean that it's very, very rigid and it acts like if they are like this? If this is infinity, that means like you don't have intermediate hinge in between. If the stiffness is very, very high, you were able to weld them together and they act like there is no intermediate hinge. But if the stiffness of this spring is 0, that means like this spring is not there. And you only have intermediate hinge. So it depends on what stiffness that you have here. Okay, so let's put this in an example. So to see if you guys understand this concept or not. Like if I have a frame like this, all right, and I put a rotational spring here. You guys tell me, I'm gonna ask you, what kind of connection that we have between this column, if you see it in a structure outside. But what I'm saying is, that's just a model of a structure. Like let's imagine this classroom and the classroom adjacent to us. Like we are here and the other class is here. We are trying to represent this structure that way, okay? So if I put this that way, this means this is a rigid connection, okay? Because they are fully connected by one single line. But in real life, this connection might be cracked. Like here, there might be cracks between the columns and the beam. So if there is a crack, that means the rotation is different. If a crack happened between a column and a beam, like this, when they are moving, that means that this one was allowed to do different rotation than this one. Like when you put load here, this one should go a little bit this way. But if this one didn't rotate the same rotation with this one, that means that we have different rotations, and this is not rigid anymore. But it depends on how much rotation difference. Some rotations you can neglect them. Like if this one like rotated 1 degree, but this one rotated 0.9999 degrees, so they are almost the same. Okay, just a little bit difference that we can't neglect it. But if I draw it that way, that means that this connection is a rigid connection. Like if this one is rotating this way, this one is gonna rotate the other way. Like they are together. We either rotate together or stay together. Okay, so that one is a rigid connection. How about this one? Is it rigid? Is it flexible? Is it semi-rigid? Semi-rigid. Why? Because what we said here. It's not perfect hinge, and it is not fully connected like this one. It's something in between, and it depends on the stiffness of this spring. How about this one?
Rigid.
Rigid, right? Because there's no hinges and there's no rotational springs. How about this one? This is a flexible connection because they allow the moment to both of them to rotate perfectly, and this one is rigid. Okay, so let me explain this in a way that you can understand it and see how this can impact the structures. I'm gonna draw a fixed beam, 3 of them. And I'm gonna put the same load on the 3 beams. Like I'm gonna put W like this. Alright, I'm gonna do 3 differences in this beam. So what I'm gonna do, I'm gonna make an intermediate hinge here. I'm gonna make another intermediate hinge here. And here I'm not gonna make anything. I'm gonna leave it that way. But for one of these intermediate hinge, I'm gonna add a rotational spring, right? Okay, this connection here at this point is rigid. This one, semi-rigid. This one is
Flexible.
flexible, okay? So these 3 differences. Let's draw the bending moment diagram on this beam. Okay, I drew the bending moment diagram here down, like the positive, I made it down, but you can draw it up. Like if you want to draw the positive bending moment like this, both of them is acceptable to me. Down, up or down, okay? So let me draw this one. This one, when there's a bending moment on this beam, is it positive or negative? Bending moment. It's positive. Because if the beam is gonna bend that way, that means it has a positive bending moment. If it's gonna bend that way, it's gonna have a negative bending moment. In Europe and Africa and most of the world, when they draw positive bending moment, they draw it down. Because they wanna make it the same shape of the bending moment. But in the US, definitely needs to be different from the whole world. So if you draw a positive bending moment and the positive need to be up, like this. So if you wanna draw a positive moment based on the US signs, you draw the positive up, means like always the positive up and the negative down. But the whole word is make it easy. Let's draw the bending moment the same shape of how's the deflected shape look like. Okay? Alright, so maybe we can switch this and make the bending moment positive upside. So if I draw the bending moment on this beam, if you have done a little bit, I'm not sure, advanced or semi-advanced structure analysis, you will find that the bending moment here shades look like this. You will have WL square over, you guys know?
Right.
12, excellent. WL square over 12. And the shape of the bending moment is gonna be something like this. And if you wanna measure from here to here, it's still WL square over 8. But from here, if you wanna find from here to here, it's gonna be different. You want to make it WL square over 8 minus WL square over 12. And when you do this, it's gonna be WL square over 24. Okay. So here, WL square over 24. Yeah, so that's how the bending moment look like. But let me ask you, if I made this intermediate hinge here, okay, how's the bending moment is gonna look like?
It needs to go to 0 at the moment where we have the hinge.
Yeah, the moment have to be 0 here, right? Because I allow the rotation. But you are gonna have a bending moment here and a bending moment here. So it's gonna be something like this. So the bending moment is gonna go maybe something like this and then goes to 0 and then a little bit here and then it goes something like this, but it has to be 0. So what we did here, we increased the negative moment and decreased the positive moment. Okay, so that's how the bending moment look like. If we did, maybe, so that you can imagine how the difference is, let me make this intermediate hinge here, in the middle. Let's make it here. Show something, and we had a spring here. So the bending moment is gonna be something like this and something like this. So can you imagine how the bending moment shifted from this and goes all the way to 0 and all the beam has a negative moment. And here's the moment to 0. But once you have a flexible, a semi-rigid connection and you put a spring, this spring is gonna have a moment, not 0, and not this value, WL square over 24. What is gonna have? Something in between, right? It cannot be more than WL square over 24, and it cannot be 0. And it depends on what? Like the value of this moment, if it's gonna be high, depends on the stiffness of this spring. The higher the stiffness, the higher the moment that is gonna absorb. the lowest the stiffness until it goes to the zero, the moment is gonna be zero here. So you are gonna have a bending moment, something like this. And this depends on the stiffness of the spring. If the stiffness goes up, the moment at this spring goes up. If the stiffness goes down, the moment at this spring is gonna go down. Do you guys understand this? Okay. So I said for a flexible connection here, I said it allows rotation and there is not any induced bending moment, and that's what we did here. Allows rotation and the bending moment is zero. And in the semi-rigid, it allows rotation, but not 100%. There is a moment, okay? So the moment is not zero. The moment equal here, if you wanna get the moment here, M is equal K multiplied by theta. The rotation that you have here multiplied by the stiffness of this spring is gonna give you the value of the moment, but you have to find how much theta that you have here, how much rotation that you have here. This is similar to the Hooke's law. Hooke's law is something, do you guys remember that B equal to K multiplied by delta? But this is if you have a linear spring, like if you have a spring like this and you have load B here, if you know the stiffness of this spring and you know how much delta that this spring got compressed, you multiply K by delta, you get P. Same thing with the moment. Moment is equal K multiplied by theta, but moment is something related to rotation, so you should have a spring like this. If you want to find how much moment in this spring, you multiply the stiffness of the spring by the theta that this spring have, then you'll find how much bending moment that you have in this spring. Okay, but this one, the rigid connection, I say it doesn't allow rotation and there is bending moment. Like, there is bending moment induced. Does any of you have any question about this? Is there anything that is confusing? Do you guys know these rules? P equal K multiplied by delta. Maybe this one is new for the moment, K multiplied by theta. But here we are, you can write it down.
Yeah.
Okay.
Can you please repeat the sign convention that you're using in this case?
What was that?
Can you please repeat the sign convention?
The sign
that you're using?
convention?
Yes.
So I'm gonna actually explain the sign convention in the first problem. Like what the sign convention that we are gonna use in the whole class, in this whole problem, just in 5 minutes. All right. Let me solve the first problem here. Example 1. Alright, we have a determinate structure. By the way, this is the only lecture that you will see a determinate structure. So take advantage of this because all the structures that we're gonna have from lectures, other lectures, gonna be indeterminate. So this one is gonna be easy. You all should be able to solve it. All right, so we have this L-shaped frame. The span is 6 meters. And this one is 4 meters divided into 2 pieces. It has different types of loads. It has distributed loads of 1 ton per meter. It has concentrated moment here, 4.5 ton meter. It has 3 ton concentrated force at this location. And what I'm asking for is find the reactions and draw, find reactions and draw the normal force diagram, the shear force diagram, and the bending moment diagram. We can say normal, shear and moment. Sometimes we say NQ and M, or NFD, SFD, and EM. That's what I want. Okay, let's just start with reactions. You can't get bending moment and shear and normal without reaction. You need to find a reaction in this structure. What kind of reaction? Actually, there's something wrong here. I said this is determinate. Is that determinate? Why? Because they have two hinges. One of them needs to be roller. Okay, so here, when I looked at the structure, I found that I did this hinge, so I need to make this rollers. All right. Okay, let's solve this structure. To solve this structure, what should I do first?
Equilibrium equation. Find the reaction.
Find the reactions. How can I start?
Sigma
The
fx, sigma
equilibrium
fy.
equation, sum of fx, sum fy, sum of the moment, okay? Right, so the reactions that we have here, as we showed on the end conditions over there, I should have a reaction here and two reactions here. Let's call this as A and this is B. I'm gonna say this is YA, XA, and YB. Let's find these reactions. The easiest one is to get
X.
sum of the forces in the
Alternate direction, x.
in the x direction. And I'm gonna assume the positive in this direction. That's the positive. Okay? So that means that's a positive. So XA is positive. The 3 ton, is it positive or negative?
Negative.
Negative. So this I'm gonna say -3, and all this is gonna be equal to 0 because there is no any other horizontal reactions. So XA is equal to 3 ton, and don't forget the units. And I would recommend this is the way that you solve in exams. When I used to take exams, I would like tell who's grading my exam, here's the answer. I box it for him, so he doesn't look all over the place, because that's what we get in the sheets. Like, you put the answer up there, and you make an arrow, and you put an arrow in the next page. So it's gonna be very, very confusing. You solve everything as simple as it should be, and you guide me to your final answer, so I can give you your full points. Okay, so first thing, we got XA. The next thing is you can either take some FYs, but it's gonna get you nowhere. Why?
You got two
Two unknowns, YA and YB. So what you're gonna have, two unknowns, you're not gonna get a final answer. But if I take some of the moments now, I take advantage that I cancel these two reactions here, and I only have one equation that have YB. And I can get YB right away. I'm not saying that some FY is bad. I'm just saying just to hold on it, so that you can get this reaction, and once you get it, do some FY, get the other one. Okay, so let's take sum of the moment about A equal to 0, and I'm gonna assume the positive is in this direction. That's my assumption. So YB is making a positive moment, and the arm of this moment is 6 meters. So I'm gonna say YB multiplied by 6. What else that I have make positive moment? I have 4.5 ton make a positive moment in this direction, so this plus 4.5. How about 3? All the loads are making moments. Okay, this, they are all making moments right now. The only load that doesn't make moment, that pass to the point that you take the moment about, like YA and XA, they pass this one. Okay, so 3 ton is making negative moment because it's this way. What is the arm of this moment? 2. 3 multiplied by 2. How about the 1? Can you guys tell me what should I write here? The 1 ton meter, the distributed load.
1 times.
So I put negative or positive?
Negative.
Negative, and then
1 into 6 square by 2.
1 multiplied by 6 so that I can get the resultant. And the arm of the moment is 6 over 2, which is 3, right? That's how I do it, like, simply, and all this should be equal to 0. Why equal to 0? Because I'm saying that this is a stable structure. If it's not stable, this is not gonna be stable. And that's the assumption of the static of structure. If a structure is static, there's no forces in X, there is no movement in X, there is no movement to Y, there is no rotation. That's why we say Fx is 0, Fy is 0, and the moments are 0. Once you solve this, you will find that Yb is equal to 3.25 ton. Okay, I'm done with this one. Then you can take the sum of Fy's, and you can assume that the positive is in this direction equal to 0. So you will have Ya plus YB, which is 3.25, minus 1 multiplied by 6 going down, and all this is equal to 0, so you'll find that YA is equal to 2.75 tons. I get all the reactions. Here, YB is 3.25, this one is 2.75, and this one is 3 tons. What is next? Once you get reactions, I can get internal forces. That's what we do. Structural engineers, they solve the structures to get reactions and get internal forces, and the structure analysis part is done. If you are gonna take this over to the next level, you are gonna use these reactions to do design, okay? So let's get internal forces. All right, internal forces, I'm gonna draw 3 drawings. So I'm gonna make one like this, and another one here, and another one here. But before I do the drawings, let's talk a little bit about the sign convention. So the sign convention, let's assume that we are gonna take a section here, okay? If I took a section, if I take this outside, it's gonna be something like this, right? It's a line because when we draw a cross section of a beam, we'll draw it as a line. But if this is a real beam, this section is gonna be something like this. If I took a piece of the beam, it's gonna be look outside. This is the length of the beam, this is the right of the beam. Like the beam is something. This is the actual frame, how it looks like. What I'm gonna do, I'm gonna take this piece and look at it here, okay? So the sign convention depends on how you look at the cross section. Do you look from the left or you look from the right? There's 2 different ways. Some people, they love to draw internal forces looking at the reactions from the right. Some look at the left. I usually use the left, but sometimes the right is easy. So I use the right to draw bending moments. So let's see what is the sign convention. Sign convention means if we are trying to figure out the sign of the normal force, shear, and moment, is it positive or negative? That's what we're trying to figure it out. So let's put it on this area. So if your section have the normal force in this way, that means there's a tension. Like the normal force is like pulling your cross section outside. That's positive. Okay? If the shear force is going up on your cross section, like you have your cross section this way, and it's going up, that's a positive. If the bending moments look like this, the tail is down and the arrow is up, that's a positive. So that's the positive direction if you're looking from the left. From the right, same thing. If you have the normal forces pulling your cross section, like making tension on your cross section, this is positive. The shear is the opposite direction, need to be this way. And the moment need to be this way. That what makes your cross section stable. How? Like if we are saying that this is positive, so that means there's a normal force that way, and there's a normal force that way, that means they cancel each other. That makes this cross section doesn't move this way. If the shear goes this way and the shear goes down, they cancel each other. Same thing with the moment. They cancel each other. That what makes this cross section doesn't move X, doesn't move Y, doesn't rotate. That's the positive sign. How about the negative? The negative is gonna be the opposite. It's gonna be, if there's a compression on your cross section, like this, or from the other side, that's a negative bending moment, negative normal force. If you have the shear goes down and the shear from the right side goes up, that's a negative. If the moment is going this way and the moment goes this way, that's a negative sign. But how we can draw them? So to draw a positive normal force, it's gonna be up. To draw a negative normal force, you draw it down. And the shear force is the same. To draw a positive, it's gonna be up. To draw a negative, it's gonna be down. Same thing is the bending moment with the US standards. You draw the positive up, the negative down. But if we are working with the whole world standards, bending moment is different from these two. We draw the positive down and the negative up, okay? But let's just stick with the US standards and draw with all positives are down, all positives are up, and all negatives are down. So let's do this. If I wanna draw a normal force, right now I knew the reactions. Let's draw the normal force diagram. NFD, or N. I wanna know how much normal force here, if I cut at this section, it only has 3 tons as a normal force, because this is a shear and the other one is a shear, okay? So the only normal force that I have is 3 tons. Is that positive or negative? Looking at this. Is this force is going inside your section or outside your section? Is it pulling your section or compressing your section? Compressing, okay? So it's a negative. So I'm gonna go down. Always look at this. I didn't look at the negative, but if it's not the positive, so it's always a negative, right? Alright, so I have this is the positive. I look at this direction, the positive direction this way, so the negative direction is the other way, so that's negative. So I go down by how much? 3, okay? If I get here, or here, or here, or here, it's always constant.
Yeah.
Because if you take a cross section and look all the loads on the left, it's always one horizontal load that is 3. So it's always constant 3. And once you draw this, you are gonna make hatching, and the hatching of the bending moment is gonna be like something like this. We draw from the line of the beam to the value here, and it's a vertical. That means like if somebody's gonna look at this bending moment, if you look at SAP 2000 or any software, they always hatch in a specific standard. That means if you are gonna measure, if I give you this paper, and you're gonna measure this bending moment, you measure it from here to here. Don't make it like this. If you make it like this, that means you don't understand anything. Nobody is gonna measure that way. Anyone is gonna measure something like this, and I'm saying it's a negative. So when you measure from here to here and you find 3, that's a negative 3. Okay, so I understand that all the normal force are negative because there is no other forces other than the 3 ton. But if I came here, it's a negative 3. How about if I came at this cross section? This 3 is not normal force with respect to this section because it's gonna be a shear force, okay? And what makes normal force is just this force. This is the only one. You can look at it from this side. So if you look at this section, that's why I'm calculating right now. What are the forces that are making either compression or tension on this cross section? This one, 3.25. Is it a compression or tension?
Compression.
Compression. Is it positive or negative?
Negative.
It's a negative, so it's a negative 3.25. If you want to calculate from the other way and look at it, you can calculate all the loads that are this way, that goes vertical. You have 2.75 and you have 1 multiplied by 6. So 1 multiplied by 6 is going down, that's 6 ton, minus 2.75 up, so it's gonna give you 3.25, and it's gonna be down as well. So that means it's compressing the section. So either you do it from the left or from the right, it's gonna give you the same answer. So this is gonna be 3.25. And it's negative, and this is how my hatching looks like. I draw the normal force diagram. Let's get to the shear force diagram. Basically, you can be done this on your own because you already studied basic structure analysis, because that's a simple frame to solve. If you have problem with solving these, I would recommend that you go study at structure analysis, frames, beams, so you can do a little bit of revision to know how to do this, because it's gonna get harder over the next week, okay? All right, so let's draw the shear force diagram, Q. What forces that makes shear here? This was making normal, that's the one that's making shear.
Yeah.
It goes up, it's 2.75, so I go positive 2.75 ton. Don't forget the units. And what happened to this shear? This shear is going down because of this load. It's going down, and what is the rate of going down? It's 1 ton every meter. So after you cut 6 meters, you should go down from 2.75 by 6 ton. So you will keep going down linearly by 1 ton per meter until you end at 3.25 ton. This is positive, and this is negative. Okay, so I draw the shear force diagram here. How about the shear force diagram here? I can do it. I will find that I have 3 tons this way, and this section is making shear this way. So I'm gonna find out that I have 3 is going this way positive, and when I cut here, I only have the 3. When I cut here, I only have the 3 until I come here. It's constant 3 until I come here, and then the other 3 is gonna take me back to 0. And I will have, this is 3, 3, and it's positive. You can do it from the other way, it's gonna be much easier. If you take the shear force here, it's gonna be 0, because there is no shear, that's a roll-up. 0, 0, 0, until you find that 3, and that 3 is going down from the right, that means it's positive. From the right, it goes down, that means you will go up. And then you will be constant, constant, until you come back to 3. So do it from the left, or do it from the right, it's gonna be the same solution. I always do it from the left. That's the easiest way for me, but maybe the easiest way for you is from the right. Okay, and here, definitely there's 0. Let's draw the bending moment. Bending moment is very, very important. That's how we calculate most of the reinforcement on the cross section. So that's a very, very important thing to know how to draw bending moments. It's a little bit difficult from the shear because you will have to do multiplications. You don't see loads that goes up and down. The loads need to be multiplied by each arm. So you pick points where you are going to calculate the bending moment. So I usually pick like joints here and the point of changing loads. Like if you have a concentrated load here, so you need to calculate moment here. If you have load here, you need to calculate moment here. So these are the 4 points that I'm gonna calculate moment at, okay? So you tell me, what is the bending moment here?
0.
0. What is the bending moment here?
0.
0, so I know 2 points that are 0. So I only need to calculate 2 points so I can solve this beam. Let's calculate the bending moment here. How can I do it? So what forces that make moment? I only have this, this, and this distributed load, so I can't calculate the moments from the left. Or I only have this, this, and this to calculate the moment from the right. You do it either way. So if you do it, you will find out that the moment here, look, I'm making at this section, right? Because it's gonna be different here. Why? Because you have concentrated moment. It's gonna change the moment. If I don't have this concentrated moment, the moment here is gonna be the same here. Okay? So I calculate before and after this moment. Okay? Alright, let's calculate the moment here. So you will find out that the moment here, you are gonna have 2.75 multiplied by 6 is gonna make a moment like this. 2.75 multiplied by 6. And you will have 1 by 6 by 3 is going down. 1 by 6 by 3. So this is gonna be 18. This one, if you calculate, maybe if you have a calculator, but it's gonna be 12 plus 4.5, so it's 15.5, right? 16.5? Okay, 16.5. I didn't do this calculation here. So the difference is gonna be 1.5, and this is gonna win, the negative moment, okay? This is the moment that is gonna win, okay? This one, so you will have a negative 1.5 down here. Negative 1.5. So the moment is gonna be something like this. Okay? So you will have, here is positive, and here is negative. Okay? So that's for this beam. Okay? Let's calculate the other side. The bending moment here is 0, and it's gonna be 0, 0 until I get here. And once I leave here, I will find the 3. The 3 starts to make bending moment. Once you go away from the 3, it's gonna make more moments. So until you will find that the moment, is it positive or negative? It's gonna be something, like if you find the moment of the 3, it's gonna be something like this. This is negative moment, why? Because the tail is up. Like this is gonna make a moment like this, which is something like this. And if I put the cross section, this is a negative moment because the positive moment from the right is this way. So you will find out that the moment here is negative 6 ton-meter. And to make sure that you did your problem right, you will find that the difference between these two is 4.5 ton-meter, which is the concentrated load here. That's what tells you if your problem is right or wrong. If there's no concentrated moment, when you calculate the moment from the left or the right or from up and down, should be the same. So that's the bending moment diagram. All right, so that's for cross section. And I want to tell you something about bending moments. Bending moments is that's what I want to say. It's very, very important for the engineer. Why? Because our enemy is the bending moment. If we decrease this bending moment, that's why people try to be innovative about their systems. They would use arches, they would use post-tension, they would use lots of different systems to decrease this bending moment. The more that you decrease this bending moment, the more you are gonna save yourself a lot of money or save your company a lot of money. The more, the way that you find system that can decrease this bending moment that are effective to implement in the construction site. So that means that you are inventing something that's gonna help decrease the cost and is gonna make you in a different place. That's why people try to invent post-tension slab, pre-tension slab, voided slab. They would invent like things, arches, all these like different types of arches, so that they can decrease the bending moment. That's why we have different systems. Why we do frames? Because of the bending moment. Why we do arches? Why we do trusses? Trusses doesn't have bending moment, it's all normal force. We need to get away from the bending moment, because bending moment is kind of like a snake. It's not pure tension and it's not pure compression. It makes tension and compression. So you need a steel and you need concrete, and you have a cracked section and non-cracked section, and it makes it uneconomic. So bending moment is very, very important thing to look at. That's why we have different systems to solve structures. So we are getting close to the end. I have a different problem that I might start with next lecture. It's about grid systems, so I'm gonna introduce grid system next lecture, but I just wanna try to make a soft introduction and a soft kick-off of the first lecture. I hope that you guys enjoyed the lecture. Next time we are gonna introduce how we can know the degree of indeterminacy about structures and teach you how to identify that. This lecture is already uploaded on Canvas. Homework number 1 is uploaded. I believe it's gonna be due in September, so we still have time. My office hours is after the class. You can stop in the 1 hour after the class. I will be in my office. But if you if you live far, or if you have other classes and you wanna schedule an appointment online, just email me and we'll try to find a spot that fit both of our schedules, okay? I hope that you guys have a good rest of the day.